Okay, so in the previous video, we took a look at taking the derivative of polynomials. And those are nice problems because they're just well defined everywhere. They're nice, smooth curves. So when you take a look at their slopes, they're really nicely well regulated. Today, what I'd like to do as a secondary piece is to look at the rational functions, the ones that are based on fractions. So let's take a look at what happens if we have a fraction-based equation. So let's start off with a simple one like f of x equals 3 over x plus 2. A very simple little idea. And so if we were to look at the formal definition, let's take a look at f of x plus h minus f of x all over h. Now, you're supposed to have the limit as h goes to 0, but sometimes we just do that work without the limit sitting in front because we would actually like to do that in stages and do AROC first, but it's all right. We're going to go ahead and do x plus h plus 2, because notice I took f of x and I replaced the x with x plus h, minus f of x itself all over h, keeping in mind I'm going all the way, the whole thing with the limit as h goes to 0. Now, of course, this problem right here is a little bit of a bummer because that's a pretty big thing to fraction bust. So I'm going to distribute an x plus h plus 2 as well as an x plus 2 through the numerator as well as the denominator. And I used this terminology a little bit last year, calling this collateral damage, because really this multiplication had to do with cleaning up the numerator and the denominator just sort of got messed up. So if we were to do that, I still have my limit. That has not changed. My denominator, I'm going to leave it alone. Now, what I'm hoping happens when we're all said and done is this original h that is my denominator is going to go away. So this should go away, and these two things right here should stay. Now, of course, when I distribute this to here, the x plus h plus 2 here and here will cancel, and all I'm going to have left is the 3 and the x plus 2. So that's all I see from this first distribution. In the second distribution, the x plus 2 cancels, and I'm left with the 3x, the 3h, and the 6. Now, on purpose, I left this minus in front because sometimes that can be a little bit confusing. But when all is said and done, I notice the 3x here and here went away. I notice the 6 here and the negative 6 over here went away. And I noticed that all I had left was negative 3h on top. And I have this h, the x plus h plus 2, and the x plus 2 in the bottom. Don't forget, there's still a limit as h goes to 0 because I haven't applied that yet. So in the final story, I now have the limit as h goes to 0. The h's would cancel, and I have x plus h plus 2 times x plus 2. Now, this is technically right here is the AROC answer. So if somebody said, hey, you know what? I would like to know the slope of this graph from 1 to 4. Well, then all I would have to do is plug in x equals 1 into this story, and I would plug h is 3 into this story, and I could actually find the slope, even in an average rate of change story, with this particular equation. However, if I wanted to find the instantaneous rate of change, all I have to do is carefully approach this as h goes to 0. And if h goes to 0, I just have x plus 2 times x plus 2, which is, of course, x plus 2 squared with a minus 3 on top. Now, again, that would not tell me the average over an interval, but it could tell me the perfect slope at any time. And one thing that I notice about this thing is this entity in the bottom will always be a positive answer. I can't even let it be 0 because it would be undefined. But what I find is it's a negative divided by a positive is negative. So this is a monotonic, a single behavior decreasing function. I can see that no matter what value, no matter any value of x that I try to plug into this thing, y, the slope of that value will always be going downhill. So that's my first example. Let's try another one that's just maybe a tiny bit harder. So maybe we had now g of x equals x minus 3 over 2x plus 1. It's a slightly more difficult problem. Now again, we're going to go limit as h goes to 0 of g of x plus h. So I'm going to go ahead and rewrite g as follows. but I took out all of the x's and I replaced them with x plus h's. So all of this stuff right here is g of x plus h in there. Now I'm supposed to subtract the original g function, which is right here, all over h. Now that is a little bit of a mess, but we're going to be all right. We're going to hit the top with 2x plus h plus 1s and a 2x plus 1, and I'm going to hit the bottom with a ditto mark. I'm going to hit it with exactly the same thing. Well, this is kind of messy, so I'm going to go ahead and write this out in a little bit of the longhand version. Now, so notice I left my h from here. I left this entire entity hoping that h is going to go away and this is all that's going to remain. When this hits this first term, the 2x plus h plus 1s, they're all going to go away, and I'm going to have x plus h minus 3 being hit by the 2x plus 1. And then on the secondary part, the x minus 3 that's left over from here, notice the 2x plus 1s would cancel out, and it would hit the 2x plus the 2h plus 1. Now, that could be easier for you than the way that I did it in class because I was running out of time, so I kind of had to go quickly through that. But now we just have kind of just a tough little algebra problem where we have to distribute all of that stuff and see what happens. So I'm going to distribute the x right here. I'd get 2x squared plus x. So I distributed this x to both. Then I'm going to distribute the h. I'd get 2xh plus h. Then I'll distribute the 3, negative 6x, and a minus 3. So I kind of finished up all of this. That's kind of a big mess. It's all of this comes from this entity right here. And then I need to come over to here, and I'm going to distribute the negative x, which is a negative 2x squared, a negative 2xh, and a negative x. And then I'm going to distribute the positive 3. So I'm running out of room again. The positive 3 would be positive 6x. The positive 3 would be positive 6h, and the positive 3. Now, that's a big line of stuff with all sorts of bad stuff happening, but if we are doing well, lots of good things are going to happen. The 2x squareds are gone. The negative x's are gone. The 6x's are gone. The 3's are gone. Let's see, is there anything else that I can see that would be gone? Well, actually kind of looks like that's all I have, isn't it? So let's see, what is left on top? Well, it looks like everything that I have left on top has an h in it. So if I factored out an h, I'd have 2 x's left here. And right here, I have 7 h's, don't I? I have 1 h there and 6 h's there. Oops, I just realized something. I can make the 2xh goes away, can't I? So let's go ahead and fix that. Let's make that go away. So out of everything that is left, it looks to me like the only thing that I have left on top is 7 h's. Well, that was a lot nicer than I thought. And so now, if we are to this stage of my problem, I can cancel my h's out. And so I could say that g prime of x would be 7 over 2x plus 1 squared, because as h goes to 0, that's 2x plus 1 times 2x plus 1, which is 2x plus 1 squared. Kind of similar to the previous problem where we find out that as this is always positive, right? So this is always going uphill, and not only that, what you could see is as x gets bigger and bigger and bigger, this entity gets closer and closer to 0 because it has a horizontal asymptote at 1/2. We learned that from last year, that it should have had a horizontal asymptote because of the matching powers. So I hope that little quick video on derivatives of rational equations was helpful. Let me know if you have any questions. All right.